So welcome back to COMP526 and now to Unit 1, the first unit that starts the real journey into our discovery of eternal truths of algorithms. I started last week by saying we want to get to these eternal truths, and they need mathematical statements. If you're only looking at a specific machine, how it's done on a specific hardware, you don't get to this eternal part. And the flip side of that is we need some mathematical models of what's going on. We need a model for the machine, we need a model for programs, and we need a model for data that the algorithms or programs work with. And that's what we'll look at today. Some of the proof techniques from last week will pop up once at some point later in the class. Today we'll mostly talk about definitions, or for this unit. So what's the goal of this unit? First of all, there's an alternative to all of what I'm saying. You could often just take different algorithms, implement them, and see which one works better. If you can do that, if you're actually in the position of doing that in an application, that might be preferable because it's the definitive answer for your specific application. But there's many caveats to this, and often you're not able to do it that way. And definitely on a broader scale, as an academic, as computer science graduates or wannabe computer science graduates, you should have an appreciation for the difference between running time and the analysis of an algorithm, and then these asymptotic complexities. I think this is just the language that computer scientists use, and so you have to be familiar with that. Then in terms of models, we have models for data, the typical ones. You might have seen those before, maybe just not under this term model of data. Look at best, worst, and average case, and sometimes more. In terms of machine models, we'll look at the RAM model, which some of you may have seen, but I'm not sure if any of you has seen the word RAM model in all its details. I like to give this in some detail because I remember when I was taught about algorithms in the simpler model, there was always a gap, and I'll come back to that gap. The word RAM model nicely answers that gap. On the other hand, it looks a little more scary than it needs to be for most of what we're doing, but I want to give this as a background. Then we'll look at asymptotic notation, big O classes. We'll see why we want to use those, and I want you to be able to analyze some simple algorithms, but nothing too crazy. So that's what we'll do in the next hour or so, maybe subject to a little break. And we started late, so let's see how far we get. Before we start talking about the more intricate models, I want to give some intuition, starting from zero in a sense, about what algorithms are themselves. And remember, we need a model for programs, but this is even on a higher level. For me, an algorithm is a sequence of instructions. That's as simple as that. It's like a cooking recipe, hence this picture. Algorithm as a term has attained a different meaning in media, etc., as some combination of a machine learning system plus implications on society, and it's often used in a somewhat negative connotation. But the meaning of algorithms in computer science is usually restricted to just this. It's some sequence of instructions that solves a problem. So we want to be a little more precise. But what I try to stress here is Facebook, for example, has implemented some system to decide what you see on your feed. And people call this an algorithm. But it's much more than just a simple set of instructions. There's a lot more going in. There's design decisions, and there's lots of machine learning and data bias, etc. So I'll try to be clear that when we talk about an algorithm, it's always this old school algorithm, in a sense, a sequence of instructions with these well-defined properties. So first of all, we want it to be mechanically executable. It should be as precise as needed to be executed on a computer. And that can be painstakingly detailed sometimes. In particular, we can't appeal to common sense of humans. That doesn't work. We have to avoid all fudge. We have to specify everything in detail. A minor thing that you wouldn't normally come across, but in some applications, it's important to make the distinction. An algorithm has to be finite in length. You can't describe how to write an algorithm where you have to write down infinitely many lines of code. It wouldn't really work well with executing that, but yeah. And a last thing is, this is a little more subtle. We want to solve not just a single instance, but we want to solve a generic problem or a generic task. So not just the addition of two concrete numbers, but the addition of two numbers in general, or at least the addition of two numbers from a certain range in general. That distinction is sometimes not so clear, not so formal, but it's usually, in the examples we'll look at, it's clear that there's a well-defined algorithmic problem, and the algorithm is trying to solve that. A typical example of an algorithm could be bubble sort, that probably all of you have seen. The underlying problem is sorting a list of data, say a list of numbers. List usually means it's given in an array, but not necessarily so. And an algorithm for me is again a bit vague. It's the underlying idea how to solve this problem, not necessarily a concrete set of lines of code that does this. So there might be a single algorithm like bubble sort, and you can write different implementations of that same algorithm. For example, in different languages, or even the same language, different implementations that are slightly more tricky and cunning in avoiding certain inefficiencies. So there's the kind of more abstract idea. That's the algorithm for me. I take that this point is a bit vague, but again, in many examples, it's kind of clear. Bubble sort, you could say the idea is that you always compare two adjacent ones, and if they're out of order, you swap them. That's kind of the essence of bubble sort, and you can implement that in many ways in a program. A second term, somewhat related, is a data structure. That's essentially some algorithms plus a specific rule how to store certain data that's associated with this. And again, yeah, this is in examples mostly is more clear what this means. And we'll talk about this at length in Unit 2. So maybe I'll leave it with that. In the main difference between an algorithm and a data structure is that an algorithm runs once. It's, in a sense, a box where you put, maybe that's something to put on this. An algorithm is a box. You feed some input into it, and then it computes, and eventually it spits out some output. That's the traditional model that we'll work with. And a data structure, by contrast, is something that sits there over time, and you can repeatedly query it or change it. You have different operations that you can apply to it. And it has a state that's preserved between those. Most of you will have seen one example, at least, binary search trees. There's many others. We'll come to that in Unit 2 in more detail. Are those basic terms clear? As always, I'll try to look at the Slido questions if you want to ask a question, or just scream. Either works. Okay, with these two preparations, let's look at what the analysis of algorithms is like. And what's it for? Why do we want to analyze algorithms? For many algorithmic problems, there are different options how you can solve it. There's different algorithms, and then many different implementations of algorithms. or in other cases, different data structures. And you would like to choose a suitable one for your task, for your application. And for us, suitable or good usually means that it's fast and maybe also uses not excessive amounts of space, but we'll focus mostly on the running time. That's the traditional objective in computer science. And in many cases, this is the core hurdle to overcome. And algorithm analysis is a way to compare different algorithms. So it can tell you, if you have two different algorithms, which one might be more efficient, which one might be faster, or in terms of space, which one is more space efficient. And also a secondary goal is it can make actual predictions, quantitative predictions about how long something will take. And that's important because it means you can then decide if a certain approach that requires you to use a certain algorithm on a certain input of a certain size, whether that's at all feasible. If the prediction is it will take 5 years of computing time, it's probably not the way to go. Whereas if it says it takes 5 seconds and you would rather have it run in 1 second, maybe that's something you can squeeze by working a bit harder on optimizing it. But if the discrepancy is so big, then you know upfront this won't work. So that's the two goals. We want to have a clean way of comparing algorithms, and we want to have a way of predicting how well would things work in a certain scenario. Now you could, as I said before, take the different options you have, implement them, and test it. And there's nothing wrong with that. The only thing to keep in mind is there are some limitations to that approach. You usually test it on some machine, and it's not clear what happens on another machine. Things can sometimes vary a lot. Then you will have to decide on some inputs that you evaluate the methods on. If you're lucky, these are representative for the application you want to use them in. If not, then you will get results that don't really tell you much. And the last point is maybe a little more important in this context. You'll test a specific implementation of the idea, not the idea itself, because you have to implement it in some concrete way to even just run it. And sometimes there's just a little trick needed to make an implementation good, and then you would get vastly different results. And the more abstract analysis can sometimes sidestep this issue. What's definitely clear from an academic perspective, this is not what we want in terms of universal truths. This is the opposite of that. It's very specific to a certain scenario, and it's not clear if it survives a certain generation of computers or a certain scenario of inputs and all these things listed here. So what we would like to focus on instead is have some more abstraction that takes away some of the specifics while keeping those that are relevant, hopefully. And by taking it into the realm of mathematics, we can prove statements. They will be a bit more abstract, but they will be proven and will never be invalidated, unlike the results from experiments. And they will give us concrete hypotheses that we can test. Because every model makes some assumptions, and we can then validate those. But it will be more clear what we have to validate. And as I said many times before, this hinges on having concrete models of machines, programs, and data. So let's start with the easiest one. I think that's the data models. You can take different approaches to this. The most versatile or most widely used ones are these. You can be very pessimistic. You always assume the universe conspires against you and gives you the worst possible input for this algorithm. That may seem a little out of this world. On the other hand, if you can prove a strong worst-case guarantee for your algorithm, you're fine, because nothing worse can ever happen. So if that's good enough, you're definitely fine. The best case is the opposite. You're very optimistic and assume you always get the easiest input. That's not usually useful for predicting running time, but it's good for looking at the discrepancy between those two. If there's a huge gap between those two, maybe the third one is interesting to look at. And that's if you average over all possible inputs, or some slightly more sophisticated models if you have a good idea for what inputs are more likely to occur in your situation. We'll usually assume, in the context of sorting, for example, we assume that every ordering of the input is equally likely, and we'll work from there. Why do people like these models? They're not necessarily the most realistic for a concrete application. But the big benefit of these models is that they reduce all inputs of a certain size to one number, to one parameter. So we usually we group inputs by size, and sometimes it's not so clear what size means, but in many examples it's quite clear. If you're sorting, it's the number of elements. If it's a graph, it might be the number of vertices and edges. Some things like this. If it's a matrix, maybe it's the number of entries in the matrix. Sometimes the number of non-zero entries. So this depends on the algorithmic problem, but it's usually relatively intuitive. So you fix the size of the input, and then you stipulate these models. So you take the worst of all inputs for a given size, or the average of all inputs for a given size. And the goal of this is to get the performance of an algorithm as a function of the input size. That's the goal. So we get a single parameter that we assume drives the complexity of an input. Like the underlying assumption behind this is if your input gets bigger, if you have more data, it takes more time to compute whatever function you're computing. And that's usually reasonable because for almost all problems, you have to read at least the data before you can do anything useful with it. And so there's inevitably some dependence on the size of the data. Okay.